Hello everyone. In this example, we'll be talking about residual stresses. And as you may already know, residual stresses occur when there is localized yielding in a part or in an object. And in this case, we have a 20 by 60 rectangular bar with a hole in it, and we've given some yield strengths to it, and we're making some assumptions. Now, because there is a hole in the bar, there's, as we discussed in the previous example, there are going to be areas in the bar which have higher stresses than the other. So that means a non-uniform stress distribution, and there's a possibility that the peak value is going to be higher than the yield strength. And when that happens, we're going to end up with some residual stresses. So in this problem, we're going to draw out the stress distribution when we apply an axial load on the bar, and then determine what the stress distribution looks like with residual stresses if the load or the stress exceeds the yield strength. So the first thing we're going to do is make some assumptions. Now, I made some assumptions in the first video when we were dealing with units, and I'm going to do it again just so you have some sort of idea of what assumptions are being made whenever we use an equation or when we use a certain design method. It's important to keep these in mind, especially when designing things in the real world, just to simplify the problem and then find a ballpark estimate of what you're trying to go for and then work around it by adding more complexities as you move along. So some of the assumptions we're going to make in this problem are, the first is that the material is homogeneous. Now what that means is you have the same material throughout the entire volume of the part, which basically says that if you take any section in the part, it's going to follow the same stress strain curve. So that gives us uniformity and allows us to relate the stress and the strain, or we understand the deformation is going to be the same throughout depending on where the stress is applied, but the material behavior isn't going to change. The second assumption that we're going to make is that the bar is initially free of residual stresses. So no residual stresses. Initially. Because if there were, then further yielding it would affect the calculation of the residual stresses that we will be making. So we're just going to assume that in the beginning, the part is freshly made and there are no residual stresses on it. Nothing is yielded, everything is still within the elastic limit of the material. And then finally, an assumption we're going to make is that we're going to use an idealized stress strain curve. So normally, the stress strain curve looks something like this, where once you reach the elastic limit, it deforms much faster, or it gets longer or shorter once you exceed a certain force, and then finally the ultimate tensile strength, and then it breaks. And what we're going to assume is an idealized stress strain curve such that it's going to have the same elastic behavior, and then it's going to be a constant value until it fractures. So what this basically says is that if I pass the yield strength of my material is going to break. And when I say break, I mean yield to a point where you lose contact, and that's going to be this X over here. So any force that gives rise to a stress that exceeds the the yield strength is going to end up in some sort of fracture. So again, this is going to be a similar procedure like we did in the previous example, where we have a bar with a hole in it, and we need to calculate the nominal stress first, and then solve for the maximum possible stress given some stress concentration factor. So the first thing we're going to do is the nominal stress. And one thing I forgot to mention in the previous video, or rather I didn't mention very explicitly, is when you're picking the point on the part, or in this case the bar, where you are evaluating the nominal stress, you want to ensure that you evaluate the nominal stress at a point where the area where you have material is minimum. So what this means is, in this case, I would take this section right here, right? Because the total area at that section is going to be less than anywhere else on the part. But that's not always necessarily true. So for example, if you had a bar that looks something like this, with a hole that's way off centered from the notch, you would have to evaluate, and let's say this was 10 millimeters, this was 10 millimeters, and this was 50, right? By observation, you can tell that this is going to be the area that you would consider when calculating sigma nominal. But when you're calculating the maximum stress at the notch, you can't use this sigma nominal. You need to evaluate the sigma nominal at this point, because as you move across the beam and you draw a stress distribution, you'll realize that things happen to clean themselves up, or the stress distribution is more uniform in this region here, right? And then it comes back to where the discontinuities would arise again. So if two features that create discontinuities are offset from each other far enough, the sigma nominal, or the nominal stress, will be different at those 2 points, and you need to evaluate them separately. So again, sigma nominal should be evaluated at the point with the least amount of material, given that the feature exists at that point. If it's a different feature that's far off, you would have to evaluate sigma nominal at that point where its area is the least. Okay, so in this case we have one feature, so straightforward, right? And we have our, let's say this is section AA, right? So we have section AA, and I'm going to draw the cross section, which is basically looks like a rectangle, and then a void due to the hole, and then another rectangle, right? And we're interested in evaluating this area here, because this is the area on the bar that's going to accumulate stress. And let's put some important dimensions on there. We need to know the thickness, so that's 20 millimeters. We need to know the length, which is 60 millimeters, and the diameter of the hole, which is 10 millimeters. And we have an axial load, so sigma nominal axial, right, is just the load divided by the cross-sectional area. The load we have here is 400 kilonewtons, and the area is going to be 20 times 60 minus 10 to give us a nominal stress of 400 megapascals. Okay, now before we move on to calculate the maximum stress, we need to ensure that the material does not yield simply based on the average stress, because if the entire material undergoes a stress, an average stress that is larger than the yield strength, then the entire material will yield and fracture. So let's say this is our original part. If the entire material yields, it will come to a point where it would look something like this. It would start necking basically, right? And this is going to fail if I keep applying the load, right? Because based on our idealized stress strain curve, if it reaches this point, it's going to fail. Like just immediately. It's just going to propagate through and break. It won't behave like an ideal part. But if the average stress were less, right, it would still look something like this, or if I exaggerated it a little bit more, maybe the hole would be a little stretched out, right? So we need to make sure that the nominal stress does not exceed the yield strength. So we had the yield strength, and again we're dealing it with tension, so it's going to be 600 megapascals, right? And evidently sigma nominal is less than SYT, and therefore does not fail. So we know that it does not fail, which means we can continue the analysis. If sigma nominal was higher than the yield strength, then we would end up with a fractured material, or it would just split apart or break apart along the plane of, the weakest plane in the system. So what we need to do now is evaluate the maximum stress and now check whether the system is has yielded or not. So we have to calculate the maximum stress now. So sigma max is equal to KT, right? T in this case again, static loading. So we have stress concentration factor with respect to static loading. Later on in the semester we'll see KF, which relates to the stress concentration factor due to fatigue loading. So that's why I put the subscript T in here. So sigma max is equal to KT times sigma nominal. And again, this is a similar procedure like the first example. We need to figure out what KT is, and this is figure 4.40b. And for that, we need to know what the D over B ratio is. So D over B is equal to 110 over 60, which is 0.167. And if I go into figure 4.4b, 0.16 is approximately here, which exactly crosses the 2.5 mark. So we have a stress concentration factor of 2.5. So from figure 4.40b, KT is equal to 2.5. And if I had to evaluate sigma max, it would be 2.5 multiplied by 400 megapascals. So sigma max is equal to 1000 megapascals. So now 1000 megapascals is significantly higher than the yield strength, which means that even though, and from our previous analysis of the average stress, even though the part does not fail, there is still some localized yielding that takes place in the rectangular bar. And this is a consequence of the discontinuities that arise due to the hole. And this is the peak value or the maximum value that the stress, at least theoretically, the maximum value that the stress concentration would cause. So because sigma max is greater than the yield strength, in this case because it's in tension, we have localized yielding. So now we need to understand how this affects the stress distribution when we load the material and then when we unload it. And for that, I'm going to draw a very elaborate diagram, and I will explain this as I go. It's important that you understand the elements of this entire diagram. There are a lot of moving parts, and be sure to understand it. If you don't, again, post in discussion board or email one of us, talk to us in office hours, and we'll be happy to explain. Okay, so what I'm going to do first, again, bear with me, I'm trying to make this as detailed as possible, is I'm going to draw the bar by itself and throw in some values such that I have some reference points. So let's say we start, okay. So again, I'm drawing the stress distribution when this thing is loaded. So we have, let's say, so this is going to be our beam. And then we have a hole in the middle. And then I'm going to draw the axes that I need. So this is going to be a stress of 0, and this is going to be a maximum at 1000. Similarly, we're going to have negative 1000, and I'm going to take intervals of 200. So I have 200, 400, 600, and 800. Similarly, negative 200, alright, and then I'm going to draw lines across the circle to show where the stress lines would not be present because there is no material. Okay. And we have a maximum stress or the yield strength as 600 and negative 600. And I think that's all the reference lines we need for this problem. Okay. So the first thing we're going to do is, using the same method we used in the first example, we're going to draw the theoretical stress distribution just from the numbers we calculated. So we have some nominal stress around 400 that goes until we hit 1000, right? It peaks at 1000. So we have something that looks like this. Similarly on this side. Alright, so this is the theoretical stress. Now, what we do now, we see that there is a significant part of this material where the stress of the theoretical stress actually exceeds 600. So we need to truncate the actual stress at 600. So anything that is beyond 600 will be at a value of 600. Right, again, 600 is SY, and this is negative SY. And the rest of the material will look something like this. Now, why is this value higher than the blue line? And the same thing over here. So let's take a step back. On the x-axis, or the horizontal axis, we have the stress. And technically, to some extent, on the y-axis, you can think of it as area. So this region here and this region here is basically the stress times the area, which is force. And in our case, we're not changing the value of the force. So the value of the force is constant. Right? And because I am dropping the value of the stress, I need to increase the area under the plot. So therefore, I will account the green line is actually at a higher value than the blue line is. And another important property when you're drawing the green line and trying to figure out, how much of it should be larger than the blue line, is this area here in light blue should be equal to this area here. Because this is sort of how much is being offset. And again, the green line here is the actual stress. Okay, so finally we can say that the stress distribution during loading, so actual during loading is in green, will look something like this. So that is part A, right? Or if I were to draw this more accurately, because it's an axial load, it would be straight lines. Again, because this is an axial load, it would be straight lines this way. So this is loading this is loading axially. Now let's look at what happens when we release the load. So I'm just gonna copy this diagram and work off of it. Okay, cool. And this will be, let me choose a different color, red. So this is unloading. So whenever you're drawing the diagram after you've unloaded the specimen, the first thing you would do is draw a line that goes horizontal from the point where you truncate the stress distribution diagram from the loading situation. So here, right? I need to make sure that I draw it at this point right here, and on the other side as well. Okay, and another important okay, so now that we know parts of the rectangular bar have yielded, we need to figure out what the residual stresses are going to be. And if your part yields in tension, the residual stresses are going to be in compression, and vice versa. If you yield in compression, your residual stresses will be in tension. And the relationship would be that sigma r, or the residual stresses, is equal to sigma actual minus sigma theoretical. And this is only when yielded. So sigma actual is equal to SY, right? It can't be greater because we already accounted for that. So where sigma A is equal to SY, at that point when you release the load, everything is going to be in compression. So, like I said, red. So in our case, we have sigma actual, which is our 600, right? Minus, theoretically, it was supposed to be at 1000. Again, I'm looking at the peak value. So that would be negative 400 megapascals. And now this just happens to be the same value as the nominal stress, but there's nothing to do with it. This 400 megapascals comes from the fact that I'm subtracting the actual value and the theoretical stress. If the theoretical stress was actually 1200, then I would have a residual stress of 600. So not to be confused with the nominal stress. So it's going to start off at negative 400, sorry. So just for reference, I'm going to draw another line. I'll draw it in red. Okay. And so it starts off at -400 and it goes up, and it's going to be in compression till basically the part where we have the actual stress at the yield strength. So it's going to end here, right? Because if I keep moving along this line, right, I'm going to keep subtracting that value from 600. So it's basically going to look like this, right? It's going to have a similar profile because I'm just doing a basic subtraction, but it's going to look different. In a sense, it's going to be negative and it's going to have different values, but the profile should look the same. So that's one important characteristic of this plot. Right, so we know that when unloaded, this region is going to have residual stresses. And now I'm not drawing lines, instead I'm bolding it, is because there is no specific direction to the stress, or there are no load lines. And this is not during loading. Now, we're not done yet, because what happens now is I said that F is equal to sigma times the area. And now in our case, because of residual stresses, this value is not equal to 0. And there is some non-zero value for the area, which means that F is not equal to 0. But we're sketching a plot for something that is not being loaded, right? The part is not being loaded, so F has to be equal to 0. So what needs to be done is if there are residual stresses, need to be counteracted by regions that haven't yielded. Right, so we want the compression side to be equal to the tension side, right? Because we want F to be equal to 0, and that only happens if the compressive stresses multiplied by the area is equal to the tensile stresses multiplied by some area, let's say A1 and A2. So we need to create there's going to be some tensile stresses as well. That need to account for it. And it's going to increase to a peak and then reduce because this value here is higher than this value here. So what's important to note in problems where you have residual stresses is if you have compressive stresses, residual stresses, and no load is being applied, there also needs to be some tensile residual stresses that counteract that, such that the total force or the net force is equal to 0. Now, if there was an additional load applied to it, the area would change depending on this equation here, right? And this another important characteristic is these two areas need to be equal. Because the area signifies the force. So this is basically the problem, right? Make sure that you understand all the elements of how to draw this diagram, and this equation is specifically very important to know what the maximum residual stress is going to be and how it's going to change over time. Thank you.